two, three. Your speaker is not working properly. What? Hello, testing one, two, three. Can you hear me? Is there anyone there? I don't know what the heck. End meeting. I don't want to end meeting. Hey, partner.
Hey.
Hello. Is there anyone there? We're plenty early. Maybe I didn't do something right. Open the something tab.
It says it's launching.
You might like this better. Here. If you want to try this one, it works better. You cannot minimize Zoom while you're recording this meeting. Okay. Open Zoom. That's what we want. I don't know if I'm supposed to sign in or not.
Did you?
I don't know if I don't remember signing into this stuff.
Did you get into the right Zoom account?
I thought I did. It says my meeting, Vince Griffin. Join audio, share screen. I don't know. Maybe I should start all over. Hey, is there anybody out there? Earth Calling Strength of Materials class. We're still early. We have 12 minutes. But they'll be logging. Start video.
Yeah,
hey, that's it.
It was just
Yeah.
share
I don't know if we need to share screen. Do we? Hey, anybody there? Start video. Hey, now that's looking good. Now click on that, and I think it'll show my whiteboard. Double click on that. Nothing happened. Okay, well, I'm going to double click on with this thing. Here we go. I'm going to go here and it's supposed to show that screen behind me here. But we made progress. Click here, maybe.
No, it says launching.
Maybe we need to just wait. Ooh, what's all that? I want that to be big. Maybe we need to call Rebecca. Click here, let's see what happens. Join a meeting.
No. Are you in your class?
I don't know. I liked what that thing said, start. So let me read that, what that says. It says, go to. It's too far away. We have to click on start meeting somehow.
So did you go into your Zoom and select the class for today or the meeting for today?
Yeah,
Oh, you did?
yeah,
Okay.
yeah, I did. I selected, hey, wait a minute.
Still just me and you on.
She's got the instructions right there behind you. Maybe we need to start over. Before we were able to click on this and I had my whole board behind me. Okay, well, maybe we should start all over. Let's start all over and do what she said there. How to get signed into Zoom.
Hey.
Hey, wait a minute. I clicked stop share and there I am.
Oh, okay. I think we're all good now.
I clicked stop share and there I am. But what about my students? I need some students.
Yeah.
That's all fine and dandy, but where?
Okay. Well, Rebecca said she was going to get on and join your class to
Oh,
see
okay.
if you were doing it right.
Yeah, I like that. That's good.
There you go.
That's really good. And today is Tuesday. I don't know what
Okay.
the heck.
Yeah,
Hey, do I hear a student?
that's Rebecca.
Oh. Tuesday, April 14th.
Dad, can you tilt the board down just a little bit?
Yeah, sure. There's a bit,
Not the computer, the board.
not the computer, the board. I don't know if it tilts down.
Down. Just a little bit.
Like that?
Yeah, there you go.
Good.
Now point the computer up just a tiny bit. Not much, just a tiny bit.
How's that?
Too much.
How's that?
No, that was too much down. Just a little bit. There
Like
you go. Like that.
Now there's a big blue R on my computer.
Yeah, you need to pin yourself.
Okay, so go up here.
Do you see the 3 little dots in the corner of your screen?
3 little dots in the corner of my screen. Chase, do you see 3 little dots?
Yeah.
Oh, there they are.
And does it say pin yourself?
Oh, okay.
Yeah, I pinned him.
Okay. Just leave that there. And then you'll only be able to see yourself.
Yeah, but now where are my students? I usually.
There's one on.
Oh yeah, Daniel.
Yeah, there's one on.
Daniel just connected. Maybe they slept in. I think my students are sleeping in this.
Well,
morning.
it's not 9:30 yet.
Yeah.
You've got about 5 minutes.
Good. Excellent. Yeah. Chase, I think maybe it's going to work.
Okay, it looks good. See you later.
Okay, see you later. Ta-ta.
Bye.
Okay, Daniel. Wait a minute. Oh, that's you, Rebecca. I see you. Okay, I'm glad Daniel logged on. Okay. How to screen share? Share screen. Go to the bottom and push share screen. Go to the file. Stop sharing button. Hey, Caitlin. There's another customer. Caitlin just showed up. Good. Excellent. We're still early. We're 4 minutes early. How to screen share. Stop sharing. There's a thing down here called screen share. I'm afraid to punch it. Go to file. Drive. Hey, Eric, we got another customer.
Hey,
Yeah. Okay. A couple of minutes before class here. If you have any questions, I'll give you 2 free minutes. No extra charge. Yeah. Hey, we got Gavin Jackson and Cameron. Welcome. You are so very welcome. Well, and Cameron is the last one there on the list. Now, if I go down here to manage participants, I can see everybody. I tell you who we got. We've got Cameron, Caitlin, Daniel, Eric, and Gavin so far. Where's all the others? Playing hooky. Maybe they'll show up here in a here's another one. No, that's Gavin Jackson again. Now, I gave you guys some actual homework that I'm going to grade, and I'm figuring out how to do it. And I believe it was on pressure vessels, actually. I don't know how many of you have tried to do that. I think maybe some of you have. Hey, we've got Kylie. Welcome, Kylie. Let me see if I've got you guys all muted or something here. This says mute all. Allow participants to unmute themselves, yes. But you can unmute yourself and answer back if you have a question or comment. Okay, well, I got roughly 9:30. I think we ought to get started. I need somebody to say, how? Yeah, there we go. We're going to get started. All right. Now, Chapter 8 is called Combined Loading. Let me talk about that for a minute. See, we've studied some important equations Long ago, we did this one here. That's the equation for a normal stress. That goes way back to January. You can find that equation on page 25 in your book. You take the normal force, you divide by the area, and you get the normal stress. It can be compressive or tensile. Then we studied torsion. And we came across this formula here. You might have forgotten that formula, but that's when you twist something. It's shear stress caused by twisting along an axis. This T stands for torque, and the rho stands for the distance from the centroid to wherever you want to find your shear stress. But I wonder if anyone remembers what that J is. Let's pick on somebody. How about it? Allison, can you unmute yourself and tell me what the name of that J thing is? Well, all I heard was nothing. So Allison didn't. Allison, are you there? Unmute yourself. Mute all. Maybe I need to unmute everybody. I don't know. This says allow participants.
Can you hear me now?
Yeah. Hey, Allison. Yeah.
Sorry about that.
Let me get this off of my screen here. And the question was, Allison, that J there, this here has a name. It's called the torsion formula. And that J has a name. Allison, what's the name of it?
It's the polar moment of inertia.
Bless you. Good going. That's exactly what it is. It's the polar moment of inertia. And there's formulas for it. And we could find them. Like, for instance, for something round, if you just had a round cross section, I think the polar moment of inertia is 1/2 pi r squared. But I don't want to lie to you. Let me double check it here. I don't want to lie to you. Yeah, no, this is wrong. It's 1/2 pi r to the 4th. That's what it is. Okay, great. Now back to my talk here on combined loading. And then we had another lovely equation that went like this. And you know the name of that equation. It's called the Flexure formula. That's the Flexure formula. And this is, well, sometimes they put a little b there for bending stress. And this is your moment that's acting on your beam. You have a beam and it's sagging. Somebody loaded this beam up and you're looking at the bending moment as a particular location. And y is the distance from the centroid. Like, for instance, if you had a rectangular beam, y is the distance from the center of the beam to wherever it is you want to find the bending stress. And I is our old and dear friend, the moment of inertia. It's not the polar moment of inertia. J is the polar moment of inertia. This here is actually the moment of inertia about your x-axis. And then you have another lovely formula that goes like this. we've we've studied all of these, and that formula has a name too. Both of these formulas deal with bending. This is chapter 6, I believe, and this is chapter 7. But 6 and 7, those chapters deal with bending. You got a beam, okay? And that beam has normal stress and it has shear stress. The interesting thing is that the normal stress in a beam is maximum at the top and bottom of the beam. And it's zero. The bending stress is zero here in the middle. Interesting. Whereas the shear stress, if you have a beam, is maximum. You've got maximum shear stress in the middle of the beam, and zero, you have zero shear stress at the top and the bottom. Interesting. And that formula is called the shear formula. Well, we've had all of those. Oh, this Q thing gives students trouble. That's called the first moment of area, and we probably need to practice that. But here's my point. Oh, we got some more customers. Look here, well, no, Kylie was here before. And there's Chris. Chris is back. Coy is here. Good going. Glad you're here. But here's my point. We have studied these as if that's the only thing that's happening. We've studied a body that only has normal stress on it. We studied a body that has torsion, it's being twisted, and that's it. But see, you could have both. You could have a body that's being twisted and stretched at the same time. Can you imagine that? And even bent. You could have, say, a rod, like a broomstick. And, well, they're kind of hard to stretch. But pretend like you're going to stretch a broomstick, so that'll give you normal stress, and twist it at the same time. That's going to give you shear stress from torsion. And put your knee on that broomstick while you're stretching and twisting, and try to bend it. And if you're bending it, you're going to get bending stress and shear stress from bending. You get all of them, all at the same time. It's called combined loading. In other words, in the real world, there's not just one type of loading. Sometimes there might be others. And I think it's chapter 8 that gives you one more kind of loading. And that, let's give you that, and then we'll work some problems here. Chapter 8 is all about pressure vessels. And if you have say you have a spherical pressure vessel. Better yet, let's say you have a cylindrical, we'll say you have a cylindrical. Suppose you have a cylindrical pressure vessel now. I know you've seen, does it say propane or butane on those tanks? You go drive in the country, go take a drive in the country, and I think you'll see, those butane tanks out there. Well, see, they're pressurized. Inside you have a gas, namely butane. And the skin of this tank, this butane tank, is being under stress, and it has, we'll draw a little stress element here. There's a stress element. It has stress going this way that's stretching it. But it's a strange thing with a cylindrical tank like that. The stress going this way is twice as big. They have a name for these stresses. This stress here is called circumferential stress. Oh, brother, circumferential. It's a big, long word. It just means it's along the circumference. See, the circumference of this tank is around and around. There she goes, around and around. And you see, this would be circumferential stress here also. Too lazy to write it out. And going this way, this is called longitudinal stress. And they show you how they derive those in your book. And I would love to go through the derivation, but I can't do everything with you. So let me just tell you what the formulas are. I'll tell you what page they are, and you could read how they got them. They're on pages 414. Yeah, 414. Okay. Well, the longitudinal stress is equal to oh, gee, it's on the page. I don't want to look. Let's see if I can remember how to do it. I think it's PR over 2T. We're on page 414. You can look it up. The circumferential stress is equal to PR over T. Now look on page 414, see if I got that right. Well, by Jove, that's what they said it is. Now they didn't write the word longitudinal on this one here, but that's what it is. It's along the axis or the length, longitudinal. It's along the axis or the length of your butane tank there. And this one here is twice as big. See, you're dividing by 2 here. This one's twice as big. The circumferential stress is twice as big. So now let's review what I've told you. We have 1, 2, 3, 4, 5, 6 kinds of stress. Some of them are normal stresses, and some of them are shear stresses. And you can have a combination of several stresses acting on your body at the same time. And they call that combined loading. Okay, well, that kind of made sense. And that's what that chapter is all about. And when you get all through figuring up each and every one of these that apply, you can put the stresses on a stress element, any location in your body you want. All right, well, there's your talk about combined loading. And now I want to go through a problem, make sure that we know how to do. I'm going to go back and we're going to review a problem in chapter 7. I'm trying to make sure that we know how to do that. That's a shear stress. But before I do, I'll open it up for any comments or questions. Does anyone have a comment or question? Gee, you're awfully quiet. Now I'm figuring out how to grade your papers that you're sending them in on Blackboard. Well, some of you, I think, have already sent in that last, it's a sort of a prototype problem, so I can figure out how to do this. And I believe if you'll go to content, you'll see that I have assigned a problem. I think it's 810. I believe it's problem 810. Is that right?
It is
I'm
it
sorry,
is
what?
prob- it is problem 810.
Excellent, excellent. And see, I'm learning how to do this. And I want you to send that to me on Blackboard, not on my email. That was driving me nuts. Yeah, send it to me on Blackboard, and I'll give you some more. I haven't figured out what yet, but I'll be giving you guys some more. And by the time I give you your final exam, you know, there's only just 2.5 weeks of school left. You'll be able to turn your final exam in, and I'll be able to grade it without going nuts, because I'll have all of your final exams for this course together in one big glob, and that's what I want. Okay, well, if nobody has any other comments or questions, we are going to tackle a problem here. It's one of those F problems, fundamental problems. It's on page 381, because I'm concerned that you really know how to do this stuff. All right, I'm going to say goodbye to this wonderful discussion here about combined loading, and we're going to do a problem. So let me get rid of this. Today's April the 14th. And this problem here is problem F71. It is on page 381. And let's go through it. Kind of hard for me to see here, but I think I can read that okay. It's really important that you get the diagram fairly correct here. Now that's going to be 200. This is a little longer. Now they said it's 300 all the way across, and these things are 20 millimeters wide. So see, this is 0.020 meters. So is this one 0.020. What's the one in the middle? It's 0.020 also. This one is 0.020 meters. Now this distance here between these, it's not 300. The 300 goes the outside, so you'd have to subtract the 20. It's 0.260. I think that distance is 0.260 meters. Because see, you'd have to subtract the 0.04 from the 0.30. Yeah, I think that's right. And then this distance here is 0.200 meters here. Now, do I have everything? Yeah. Now here's what they want. Now wait a minute, Auga. They want us to find at a point right here, they're going to call that point A. They want us to find something. What do they want us to find? The shear stress. To find it, we're going to have to go VQ over IT. That's what we're going to have to do to find that shear stress at A. And they said this distance here is 90, 0.090 meters. Now, does that make sense? Let me think. Well, halfway would be 0.10. Yeah, it kind of makes sense. See, if you went to the middle here, see, that's point A right there. If you went to the middle, you know what that would be? That would be 0.100 to the middle. But they're not going to go to the middle. They're just going to go 0.090. I hope that made sense. Well, we're ready to work on this. And what are we going to find? The shear stress. That's what we're going to find. Okay. First thing we got to do is get this moment of inertia. Now, do you understand this? We're used to having beams, you know, like these I-beams that are like this. But this beam's on its side. It's being bent about this axis here. And so to get, what we want is the moment of inertia about the x-axis, which is through here someplace. See, the x-axis goes through the middle. I need just some little bit of feedback. Mohammed, you're my friend. Say uh-huh. Mohammed, earth culling Mohammed, come in, Mohammed.
Oh, yes, Professor.
Thank you, Mohammed. I feed off of you guys. If I don't know you're there, it kind of bothers me. But you're all there. We got a good class here. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Whoa, lost track. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We got 12 wonderful students. And we're going to find the moment of inertia. Here we go. All right. Well, we're taking the moment of inertia about this x-axis. That'd just be 1/12. Let me do this body here. That would be 1/12 times 0.02 times 0.2 cubed. And you're done. That's it. We don't need the parallel axis theorem, do we? And there's 2 of them, so instead of writing that over, I'm too lazy, I'll just multiply by 2. Now we got this one and this one, we're done, and now we're going to do this one. That should be 1/12 0.26 times 0.02 cubed. And again, we're taking it about its axis, its centroidal axis. I think that's it, guys. So let me do that. I'm going to see what I get for the moment of inertia. You do it too and see what you get. Well, I got this answer. I wonder if it's right. I wonder if that's right.
That's what I got.
Yay, there's two of us. Good going. You know what? I think we're doing great. Okay, well, we got that. So I'm going to circle that. We know it's about the x-axis. There we go. Now the thickness, we'll get to that in a minute.
Excuse me, Professor.
Sure.
Shouldn't we need to use the parallel axis theorem if we're finding it specifically for point A?
No, we need the moment of inertia for the whole beam cross section. Point A's got nothing to do with it.
Okay.
We're going to need to talk about that point A when we get to this Q thing, though. It's going to make a difference when you find that first moment of area, but not for the moment of inertia. I think we're fine. Okay, now next, V. I think they give you V. Read the problem. It says V is 100 kilonewtons. We'll just draw it. Here it is. There it is. V is 100 kilonewtons. So we'll circle that. We got that. Now let's get this Q thing. Now, do you guys remember how to do that Q thing? I gave you a step-by-step plan. What you do is you draw a line through the place where you want to find your first moment of area. I wish I had different color pens. My daughter's going to get me some. She's going to order me some. But you draw a line through there, and here's the line. It goes right here, and it just goes right along the top of this. It goes right along the top of that, ding, like that. And then do you remember the next step? You color in the stuff above the line. I'm going to color in. That's why I needed some different colors like blue or green or something. And then what do? Well, you find this Q thing. Well, the Q thing, they call it the first moment of area. Technically, it's written like that, but we don't need to integrate anything. It's just rectangles. So you could write this as the sum of the y bar A. That'll work. Okay, now this y bar thing is the distance from here to the middle of this. I'm going to have to think about that. I think it's 0.045. So it's 0.045 meters times the area of that thing, which is 0.090 times 0.020. But since there's two of them, you got to multiply all of that by 2, and we should be done.
Where did you get the 0.045 again?
It's the distance. Remember, to find this Q, you draw a line. They want to find it here, so you draw a line through there and color the area above the line, and then go to the centroid of that area. And since it's 0.09, then halfway is 0.045. That makes sense?
Yes, thank you.
Yeah, anytime. Thanks for asking. I love knowing somebody's out there. Gee, we got a great class here. Yeah, there's Chris. Chris is here. And Coy, yeah. Got a great class. Okay, well, I think that's it, guys. So let me do that. I'm going to find the, they call it the first moment of area. Here we go. 0.045, 0.09, 0.02 times 2. Well, I'm getting 1.64, no, 1.62 times 10 to the -4 meters. It should be meters cubed. You know it? It's meters cubed, isn't it? I wonder if that's right. It's wrong. Now here's where I made my. This is wrong. When you're doing this, this has got to be from the centroid of your cross section of your beam. I put the wrong thing in there. Shame on me. What I need is this distance here from the center of the. See here's your centroid of your whole beam, okay? And this distance here must be from the centroid of your whole beam. And so you have to go from here to here. And I think I have to add another 10 millimeters. So this here is going to be, this was wrong. This should be 0.055 meters, but the rest of it's right. And you'll get a different answer. We're going to get the right answer now. All right, here we go. We're going to get the correct answer. This is a common mistake that students make and instructors. That distance there is the distance. It's the distance to the centroid of your body from the centroid of your cross section of your whole beam cross section. Okay, well, here goes. I'm going to do it now. 0.055 times 0.090 times 0.02 times 2. Okay, I think maybe the answer is 1.98 times 10 to the -4 meters cubed. We think we have Q, and we think we have it correctly. Now, if we can just get this T, that T is the thickness. Well, if you're doing it here at point A, the thickness, you've got two little thicknesses to worry about, there and there. I think the thickness, here, I'll write it for you. I think the thickness is 0.04 meters. We're talking about these two areas here where A is at, above A, 0.04 meters. Okay, look at here. We've got all, well, everything we need. We're just going to put it in our calculators, and we're going to solve for the shear stress at A. I think that's what they wanted, isn't it? Yeah. Okay. If you know all four things, put them in your calculators, and let's see what we get. Here we go. Okay, and then you have to divide by the I. And then divide by the 0.04. Well, I got an answer. Here's what I'm getting. I'm getting 18.44 megapascals for the shear stress at point A. Okay, great. Wasn't that fun? Now let's look up and see what they said. This was F7-1. Okay, I'm gonna look it up and see what it says back here. F7-1. Now they said, the book answer says, the shear stress at A is 18.4 megapascal. Hey, Shazam. That's what we got. Look at there. I guess they just sort of lopped off that other 4 there. That's how you do it. Go ahead.
Real quick, Professor, where did you get the thickness again?
The thickness. They wanted at A. Well, see, A is right above here, and you've got 2 thicknesses here. You got a 0.02 and a 0.02, so the thickness is 0.04.
Okay, so it's the entire thickness at
Absolutely.
that what do you call that, plane?
Yeah, it's the thickness. If you slice it there, if you slice that there with a skill saw, there you go. The
So you're
thickness is,
including even the right-hand portion when you're
yes.
doing that?
Yeah,
Okay.
you got to include them both. Yeah.
All right, thank you.
Thank you for asking. Okay, well, now that was loads of fun. Was there any other question on that? All right. Okay. I want to do another problem. That was a chapter 7 problem. Look, kind of a little bit of a review here. I just want to nail down the make sure you guys understand this stuff. I want to do a chapter 6 problem. Let's see if I can find what I want here. Yeah, this looks pretty good. Yeah. Okay, now this, if you're happy, I'm going to erase all this and we're going to do a chapter 6 problem. Unless there's any objection, but here's your chance to speak up if you have any other comment there. Okay, well, I'm going to say goodbye to that problem. It was a lot of fun, wasn't it? Notice, even though I'm kind of sloppy, I'm doing the best I can. You should be doing this to scale with a ruler, and you should be drawing it to scale. And can you see how important a good diagram is? I just about fouled up that problem because I got the wrong distance, didn't I, at first? But if you draw an accurate diagram, maybe you can prevent screwing up. That's the plan anyway. Try to draw an accurate, scaled diagram. Okay, now we're going to try another problem. This is from chapter 6. It's problem 6, 164. 6/164. I see it there. I don't know if we've done this before, but if we have, it won't hurt us to do it again. This is 6/164. It's on page 356. I tried to draw it to scale. This one's in inches. Now, what do they want us to do? They're giving us that this beam is made out of A36 steel, which means that the yield strength is 36 KSI. Okay. Great. And what are we supposed to find? We're supposed to find the well, here's some things we're supposed to find. I think we're supposed to find the I don't know if you remember these. We studied those here recently. This here is called the maximum elastic moment. We're supposed to find the maximum elastic moment. If you apply a moment bigger than that, did that all get? Yeah, you can see that. See, if you apply a moment bigger than that, then you start going plastic. Now I want to see if there's anybody that listened to me when I told you about this. We're going to figure this here in a minute. And let's say you do go over that maximum elastic moment. This cross-section of this beam will start to go plastic, but where? Here, let me pick on somebody. Eric is a good friend of mine. Eric, unmute.
All right.
And tell the crowd of wonderful classmates where this thing will start to go plastic. Eric, where does it start to go plastic?
Would it be, I'm not 100% for sure, but I'm thinking the centroid, maybe?
Nope. That's not where it starts. But thank you for trying. Try again. We'll give you 3 guesses. Try again.
Then would it be the outsides, like?
Yeah, Eric, it's going to be at the outside. But where on the outside? Hey, let me give Eric a hint. Eric, there's an equation that goes like this. See, this is fun for me when I have some interaction with my students. Now, this has got a name. This formula is called the Flekscher formula. And if you wanted the maximum stress, I mean, I is just going to be a constant. The M is going to be the what they call the maximum elastic moment. But can you see you're going to get the maximum stress where the y is maximum? Now, Eric, if you can tell me where that y is maximum, you can win the prize. Where is that?
Let's see. So it's as far away as it can be from the centroid.
Yeah, and where will that be on this cross section?
I would say the bottom.
Yeah, he got it. Yay, Eric, you get it. Whatever the prize is, you just won it. Now, what we're going to have to do is we're going to have to find where the centroid is. And it's not here in the center of this thing. And it's not here in the center of that thing. Those are the centroids of those parts of that cross section. But I tell you what, it's kind of in here. And Eric says the y will be maximum at the bottom because look at here. This distance from here to here, oops. That's your y distance. And it's bigger. Can you all, y'all, a little Southern talk now. Can y'all see that y there is bigger than that y there? It's bigger, isn't it? And so you'll get your maximum stress at the very bottom. And the very bottom will start to go plastic. And you'll have a region here, I don't know, kind of like that, a little thin layer of plastic. There'll be a plastic region down there. It won't happen up here yet. If you keep increasing the bending moment, if you make this bigger and bigger and bigger, you'll even get to where there'll be a plastic region up on the top too. In fact, if you make it big enough, they call this the fully plastic moment. And they want us to find that, I think. Isn't that what they want? Let me read this again. Maximum elastic. Yeah, that's what they want. This is called the fully plastic moment. Fully plastic moment. We're going to find those. We're going to find them. But before you can, you have to find the centroid of the whole cross section. Now we're kind of lucky since these both have the same area. They're 3x6s. That'll put this thing right smack dab in the middle. But using the formula for centroids here, I'll write it out. Here we go. We're going to find the centroid. We're going to measure from here. And what you do is you go up to here. That distance is 3 inches. And you multiply by the 18 square inches. And then you go up to here. And that distance is 7.5. And that area is also 18 square inches. And then you divide by the area of the whole thing, which is 36 square inches. And what you come out with is, you guys go ahead and do that. I'm getting 5.25 inches. That's where the centroid of this whole thing is. This distance from here up to here is 5.25 inches. Now you could have done that a lot easier. You didn't need these 18 square inches. You could have just taken 3 and 7.5 and divided by 2, and you would have gotten your 525. Did that make sense? Probably not. But it's halfway. it's going to be halfway in between if these areas are the same. Okay, now we've located our centroid of our whole piece. So I don't need that stuff there anymore. I know where it is now. I know where it is, but we're going to need this distance here. And that distance there is 525 minus 7.5, I think. That distance is, I can't do that in my head. I think it's 7.5 minus 525. I'm getting that distance is 225. And we're going to need this distance here. See that distance right there? Well, it'll be the same because it's right smack in the middle. That distance is 225 inches. What it would be 525 minus 3. I can do that in my head, 225. Okay. Now we're going to solve for the maximum elastic moment. And what we're going to do is we're going to use this equation here. Only we're going to put in the yield strength. And we're going to put in the maximum elastic moment. Now I know there's a minus sign there. Put absolute values on there if it'll make you happy. And we're going to put in C, which stands for the maximum distance from the centroid. I just had a senior moment. Did we ever figure out what I was? I don't think we did.
No, we didn't.
No.
Yeah, you kind of stopped halfway through.
Did I get started on it? See, here's what we're going to do. Now, I know what this is because they told us it's 36 KSI. And I know what this is because Eric and I discussed that. That's going to be that 525. That's the largest distance from the centroid to the outside. This is what we're solving for. If we only had the moment of inertia for the whole piece, we could do that, and we could get this maximum elastic moment. Okay, well, here goes. We're going to do it now. We're going to get the moment of inertia. And here's how you do it. You go 1/3 or 1/12, 3 inches times 6 inches cubed. But see, that would be if you had this thing about its center, and it's not. You've got to add to it the 18 square inches times that 2.25 squared. It's the parallel axis theorem. Now we're not done yet. I've just done this piece. I've got to add to that 1/12, 6 inches times 3 inches squared plus the area of the top piece, which is 18 square inches, times that distance there, which also happens to be 2.25 squared. We got to add all this jazz up, and we will get the moment of inertia. Okay, I'm going to do that. You do it. I'm going to do it. For anybody that just tuned in, hey, there's another customer there. There's Ross. Welcome to the program there, Ross. For anybody that just tuned in, we are doing 6-164. It's on page 356 in an effort to review these concepts, maximum elastic and fully plastic moments. Okay, here goes. Okay, I did all that and I got an answer of 240.75 inches to the fourth. Wonder if that's right.
I got 249.75.
Yeah, you're right and I'm wrong. I must have done something wrong. Let me do it again. My numbers are all correct. I just pushed the wrong button. I'm going to try again. But you got the right answer. I'm plugging all this stuff in here. Gee, I got the same doggone answer again, but your answer is right. Let me do it again slowly here. I'm doing something wrong. Oh, here's what's wrong. That needs to be a cube right there, guys. Do you see that? That's wrong. That needs to be a cube, doesn't it? Somebody say, oh. All right, now this time I'm going to do it right. I had the wrong number in there. No wonder it was wrong. Okay, we're trying again now. Okay, now I'm getting the right answer. It's 249.75. That excellent student that just spoke up got that right answer. They must have put in the right equation and they didn't follow my wrong equation. Okay, now let's see what we got now. Hey, looky here. We got everything we need to solve for the maximum elastic moment. All we got to do is plug and chug now. And that's what I'm going to do. I'm going to multiply and divide and get my maximum elastic moment. Here goes. Well, I got an answer. I'm getting a maximum elastic moment of well, now these are
They're in mega
mega.
pound inches.
Yeah. I tell you what we could do to make it fancy wancy. KSI? No. Kip inches. There we go. Because it's a moment. Yeah. I think that's right. Those are in kip inches. Now we can get it in kip feet. Divide by 12. I'm going to divide by 12. And what you'll have is you'll have 142.7 kip feet for the maximum elastic moment. Okay, great. Now, if you exceed that, if you put a moment on this thing bigger than that, then you start going plastic down here at the bottom. And then if you keep getting a bigger and bigger moment, the whole thing will go plastic. And let me show you what happens when the whole thing goes plastic. See, right now, this is the centroid of the whole piece. And I've told you guys this. Above that centroid, you have compression. And below that centroid, you have tension. Do you remember me telling you that when you have a beam, it's got compression on the top and tension on the bottom? Well, as long as it's elastic, above this centroid, you have compression. Below the centroid, you have tension. Right at the centroid, you don't have tension and you don't have compression. There is no stress as long as it's elastic. They call this the neutral axis. And as long as it's elastic, the neutral axis is the same place as your centroid. But when it starts going plastic, you start off with a small region that's plastic down here, and it starts growing on you, and it gets bigger. And if you keep your moment getting bigger and bigger, you'll start getting a region of plastic region up here, and it grows on you and it grows on you until the entire cross-section of your beam is plastic. Now, the way it works is in this class, the sum of the forces is still got to be 0. And the force is going to equal stress times area. So the force on this top area will be compressive. It'll be pushing like that. And it'll equal your yield strength times that area, which happens to be 18 square inches. And the stress on this bottom area will be equal to that. It will equal to the yield strength stress times that area, which is 18 inches. What I'm trying to tell you is the neutral axis shifts and it goes to here. When it goes fully plastic, as you keep increasing this bending moment acting on this beam, the neutral axis moves up until finally, when it gets here, it's fully plastic, and the neutral axis is there, where these areas have to be the same, because the force yield strength times area going in compression and the force in tension going that way will add up to 0. And now we can get our fully plastic moment. Do you notice we have two forces that are equal and opposite? What do they call it when you have two forces that are equal and opposite? We'll pick on
Newton's third law.
That was intelligent, but Newton's third law refers to two separate bodies. The one body has a force on the other body, and that body has an equal and opposite force on that body. What we're talking about here is just one body. We don't have two bodies. We just have one body. And what I was trying to talk about is the sum of the forces on that body have to be 0. And they will be 0 if your neutral axis divides the total area exactly in two, where the areas are the same. Because the forces are the yield strength times the area. And the areas are the same, top and bottom, for this particular example. Now, what I was asking my wonderful student was, when you have two equal and opposite forces separated by a distance, they have a special name for that that we know.
Coupling.
That's it. It's a couple. Good going. It's a couple. And if I only had some room here, we could write that couple. We'll make room. There we go. There's plenty of room right in here. We've just discovered that the fully plastic moment is a couple. It's separated by a distance. Now I'm going to have to think about what that distance is between these two forces. If I had some red, my daughter's going to get me some red, I would paint this one red, and I would paint this one red. And so we have two forces, equal and opposite, separated by a distance. But what is that distance? Well, it's 4.5. Can you guys see that? It's 4.5 inches, and this here is 36 KSI times 18 square inches. And so is this. It's your yield strength times your area. The area is 18 square inches of the bottom piece. The yield strength is 36 KSI. And so the fully plastic moment is going to be 36 KSI times 18 square inches times 4.5 inches. Okay, here goes. Right now, for those of you that just woke up from a daydream, we are doing problem 6-164, and we're getting the fully plastic moment. Okay, here goes. Well, I'm getting a humongous number. I'm getting 2916 kip inches for the fully plastic moment. If you divide by 12, you can get kip feet. Let me do that. I'm getting 243 kip feet. We just figured out the fully plastic moment. Now let's look and see how we did.
Can you explain how you got the 4.5 inches again?
Oh, sure.
It's the distance between the two centers of mass of the bodies, right?
Right. And we found this distance is 2.25. We found that distance is 2.25.
Okay, that makes sense. Thank you.
You got it? Thank you for asking. Now let's see how we did. This is problem 6-164. Let's go shopping around here and see 6-1. Now what they said was the fully elastic, maximum elastic moment is 143. The book got 143 kip feet. If you look in the answer book, 6-164, and I got lost there, 6-164. I don't see it there. Oh, no, we're doing 6-165. Sorry to lie to you guys. Really the problems are the same. It's 6-165. What's different about them? Not much. 6-165, you got 143 kip feet. Now the fully plastic moment, they got 243 kip feet. Hey, the book got 243 kip feet. We got what the book got. Now I'll show you some more fun things about this problem, but first, did you have any comment or question? Anybody? Well, nobody said anything, so I guess you're all right. Now, there's a few other things that I told you guys here recently. I just need a little room to do that. Where can I do that? You guys, we'll just say goodbye to my lovely picture here. There's a few other things that I told you guys. One of them was K, the shape factor. What the shape factor is the ratio of your fully plastic moment to your maximum elastic moment. Well, in this case, it would be it'd be 243 divided by 142.7. Okay, let's see what you get. They call this the shape factor. It's dimensionless because it's just a ratio. Okay, 243.
1.703.
I almost had it here just a minute. 142.7. 1.703, something like that. 1.703. There you go. Now, if you just had a rectangle, I might have told you guys this, I don't remember. If you just have a rectangle, the shape factor is 1.5. Now, I don't design buildings, so talk to somebody that does if you want to learn more about the shape factor. But I do know it's 1.5 for rectangles. But see, this was not a rectangle. This was sort of a T-shaped thing. Now, there's something else I told you guys recently, and that's called the section modulus. And it's pretty nifty. It has its uses. Actually, the fancy name for it is the elastic section modulus. And there's two equations for it. Let me give you those and we'll solve that. Just need a little room here. We don't, I don't know, I might need some of that. Yeah, I better not erase it. One equation goes like this. Kind of rusty here. It's just the moment of inertia divided by that C, which is, remember, C is the maximum as far as you can go to the outside of your piece from the centroid. Okay, well, let's see what that is. Here's your moment of inertia, 249.75. And, oh gosh, I forget what the centroid was. It was it
5.25.
Yeah, 525. Now this is inches to the fourth, and this is inches. So you're going to get inches cubed for the elastic section modulus. And here we go. I'm going to do that now. Okay, I'm getting 47.57 inches cubed. Need a little room there. It's getting kind of messy right in there. Now there's another equation for the elastic section modulus. Let me give you that. It goes like this. The other equation, it goes where this here is our old friend, the maximum elastic moment. And we figured out what that was. Probably ought to leave it in kip inches. It's 1712.6 kip inches. And this one was 36 KSI. Put that in your calculators and let's see what you get. So 1712.6. The kilos cancel, don't they? Divided by 36. I'm getting 47.57 inches cubed. Well, shazam. That's what we got using the other equation. Both of these equations are good to find the elastic section modulus. Now I'm going to give you one more thing here that's not in your book. No extra charge. No extra charge on your tuition. And I need a little room here someplace. I bet I could use this room here. And this little guy here is called the plastic section modulus. And there's two equations for it. One of them goes like this. Where you take the shape factor, which isn't 1.5. Remember, that's for a rectangle. Forget that. Our shape factor is 1.703. It's just a dimensionless number. Times your elastic section modulus, which is 4757. And you can get your plastic section modulus. I'll show you what good it's for here in just a second, but there's another equation that goes like this. Should give you the same answer. Where you take your plastic section modulus. Gee, I think I erased it. Dang. You take your plastic section modulus, which is
The 243 kip feet.
oh, bless you. Yeah, it's oh gosh, it's 243. It's 243 kip feet, wasn't it? Yeah. Or in terms of kip inches, it's 2916 kip inches. If you divide that by 12, you'll get the 243 that my friend just mentioned. And then you divide that by 36 KSI. Try that and let's see what we get when you do that. 2916 divided by 36. Well, I got 81. 81 inches cubed, right? What's this when you multiply that? We never did do it, did we? 1.703 times 47.57. Boy, Jove, you get 81 inches cubed. Either formula is good. Now, what good are they? Well, here's what they're good for. I got a little room right in here. I can write right in here. See, if you know what the elastic section modulus is, you can get the maximum elastic bending moment by taking by taking your elastic section modulus and multiplying by your yield strength. And similarly here, you can get your fully plastic moment by taking your elastic section or your plastic section modulus and multiplying by your yield strength. All I did was just a little tiny bit of algebra to this equation. Yeah. And to this equation here. Yeah. And see, this is a warning here. It's a warning. You don't want to put a bending moment that big or bigger. Is that how you spell warning? Yeah. Because if you do, you're going to start to go plastic. It's kind of like a first little hint of problems. Now this is a severe warning. It's also a warning, but it's a severe warning. If you know your plastic section modulus times your yield strength, you can get your fully plastic moment. That's your whole beam collapses. It collapses. And see, the thing is, there's tables of these things. You can look these things up, especially this. I showed you that in the back of your book. There's page after page after page in the back of your book, if you look hard enough, of elastic section moduli. Okay, well, let's see how we're doing. Oh, gee, it's so sad. Our time is coming to an end, and we've had so much fun. And if you'll read the content on Blackboard, I gave you a homework problem, and that one I'll be able to grade in Blackboard. I want you to send it to me in Blackboard. See if you can figure out how to send it to me in Blackboard, and I'll grade it and give you 4 points, I hope. But I'm learning how to grade stuff on Blackboard. Now, is there any last comments or questions? The floor is open for your questions.
Hi, Mr. Griffin. This is Corey.
Hi, Coy.
I have a question. So all the homeworks that you gave us last week is
Yeah,
not.
you don't give them to me. I don't want them.
Okay. Okay. Thank you.
They're just for your enjoyment, Coy.
Okay. Thank you.
You are so welcome. And I'm trying to post the answers to those because I want you to know how to do those. Hopefully I did post the answers to those problems that I gave you. But I'm not going to post the answer to this homework that's going to be due, I think, Thursday night at midnight or something like that. I won't post it till probably Friday. By that time, see, you'll be late, and it'll be too late to turn that in. Well, hey, look, you can still turn stuff in and get a 2. Isn't that our deal? Yeah, you can turn stuff in and still get a 2, but if you want a 4, you have to turn it in before the due date. Anybody else? Coy had a good comment. Anybody else? I don't hear anything, so I'm going to figure out how to push the button to end the meeting. Here we go. I'm going to end the meeting. Goodbye, everybody.
Thank you, Professor.